start the recording, and I'm showing you the wrong screen. Okay, hold on a minute. Get things in order here. Okay, I think you can see the PowerPoint.
Yes.
Is that right? Okay, very good. So today I plan to discuss chapter 30. I think that's what you guys are talking about in class, right? I hope.
Yes.
Okay, very good. Nuclear physics and radioactivity. And as usual, I'll give you my take on things and I'll work out a couple examples. So at the end of the 1800s, late 1800s, excuse me, people were starting to be convinced that things were made of atoms. It was not decisive until 1905 with Einstein's description of Brownian motion. But increasingly, people were believing it because some very good results were coming out. But people didn't really know what the structure of an atom was. Sort of the best guess, the simplest guess is that I think the famous phrase is plum pudding from I think Thomson. The idea was that an atom is just sort of a mixture of positive and negative charges, as if you were looking at plum pudding and the raisins or the protons. And Rutherford did an experiment where he bombarded some gold with some alpha particles. We'll talk about what alpha particles are. And according to the theory, he should not have measured very many things being deflected. There should have been some deflection of the alpha rays, according to the theory that was developed. But instead, he got a huge signal of alpha particles coming right back at him. There's a famous quote, which I don't remember right now, but it was as if it's something, he described it as something like it was as if he threw a baseball into an empty room and it flew right back at him and hit him in the head. In terms of calculations, the predicted value was off by a factor of 1,000 or something like that, some tremendous number. Anyway, the upshot of Rutherford's experiment is that the atom consists of a really, really tiny, very dense part in the middle and mostly empty space. And the electrons are out there somewhere. Vastly, vastly different than the plum pudding model. Okay, before I go on, I have this reminder here that there's a student evaluation of teaching, which is now open. I should have shown you this before. So this is how you do evaluation of me in particular. There will be a form where you can fill out and evaluate my teaching. That's separate from the lecture where you have a different form for that. So I am told that you will receive a notification via email and within Blackboard, if you haven't already. And there's a link that you can go to log in and do this. Here's the link where you can go and log in. If you have questions about how it's to be done or frequently asked questions, you can go to this, excuse me, this webpage here. And let me ask you to please do this. Last semester, not enough students did this, and the results are, the plan is to basically discard the results from last semester because not enough students did it. So I would really appreciate it if you could do this. Of course, I would really appreciate a good evaluation. But nevertheless, please do this. It would help everybody. And in particular, I've added some specific questions to my questionnaire at the end, just to get some specific feedback on things I did in the recitation. Okay, going on. So at this point, we know that the nucleus is a really, really highly dense part of the atom in the middle. And what is it made out of? It's made out of nucleons. You know this already, I'm sure. It's made out of protons and neutrons. Protons carry 1 unit of positive charge. Neutrons, as their name suggests, are electrically neutral. And the number of protons present in the nucleus is what determines the element. All right, so it turns out that nuclei of a given element can occur with different numbers of protons, and they're called isotopes. So, and here's some notation for an element. So X is the element symbol. A, or at the Z at the bottom there, the subscript that precedes the element is the atomic number. That's the number of protons. And so that determines the element. It's a little bit redundant, perhaps. But one needs to know the number of protons in the element. And then A is the number of nucleons, and that's the sum of the number of protons and neutrons. Was there a comment in the chat?
Yeah, there's a question that said, I thought isotopes had to do with changing neutrons.
Yeah, that's right. That's what it says. So nuclei of a given element can occur with different numbers. Oh, I see. Yes, it's a typo. Thank you. Neutron, no, not neutrons. Neutrons. Yes, thank you for pointing that out. As a typo, of course. Nuclei of a given element can occur with a different number of neutrons. Those are isotopes. Of course, an element is defined, as I just said, the number of protons. So, for example, you have carbon-12. That's the standard carbon that one finds. But there's also a version, carbon-14. Carbon has 6 protons. That's why it's carbon. But carbon-14 has an extra 2 protons as compared to carbon-12. All right, mass of these things. So mass of a proton is this. The mass of a neutron is this. They're very close, slightly different. The neutron's a little heavier, but it's basically 10 to the minus 27 kilograms. They're tiny. There are other units for mass that are more convenient. So the unified atomic mass unit, in other words, U, lowercase u, by definition, carbon-12 has a mass of 12U. Exactly. That's by definition. And so 1U turns out to be this number, 1.66, whatever, 10 to the minus 27 kilograms. And sometimes you're going to see masses given in these strange units, MeV over c squared. So how does that make sense? Well, because E equals mc squared. So we didn't do the chapter on relativity, but I did point out last week that mass is equivalent to energy, and this is how they are equated. So if you just solve this equation for the mass, you can express the mass in terms of units of energy divided by c squared. And so that's why it's written this way. So mega electron volts. So electron volts, you know, are units of energy. Mega electron volts is million electron volts. So that's what's in the numerator, and then divided by c squared to make it into units of mass. Okay. And here's the conversion from one to the other. So 1U is this many kilograms, and it's this many mega electron volts over c squared. And you'll see all of these. There's a chart in the book that tells you the masses of these various things in terms of kilograms, U and MeV over c squared. Basically, the proton and the neutron and the proton and neutron are very similar in mass, as you can see. The electron is tiny. In the middle here, there's the 1,1 hydrogen atom. So that's a proton plus an electron going around it. So you see this number is, if you add these two numbers, you get that number, basically. So the thing to remember is that a proton or neutron are about 2,000 times as massive as the electron. You could say that the proton and neutron are about 1,000 MeV per c squared, and electron is half of 1 MeV per c squared. All right. The nuclei, the nucleons in a nucleus, basically pack together like hard spheres. And so given that geometry, you can estimate the radius as this. So it's this number, is a really tiny number, times A, the number of nucleons to the 1/3. So as I mentioned, if you just take billiard balls and pack them together, you expect the radius of that pack to go up like the number of billiard balls that you have to the 1/3 power. So this suggests that they're kind of behaving that way. And notice that this number is really tiny. An atom is usually estimated to be about 10 to the minus 10 meters in diameter. And so this is 5 orders of magnitude smaller. So that's what A is. So the nuclear density, since they pack together basically without any overlap, the nuclear density is essentially constant. Now, it may seem obvious because we think about these things as particles, but remember that particles have wave properties as well, and they're very pronounced when you're talking about things that are so small as this. So it's not entirely correct to think about them as just particles. They're really particle wave things. But nevertheless, the nuclear density is essentially constant, meaning independent of the number of nucleons. Now, interestingly, the nuclear density is about 10 to the 15 times that of ordinary matter. That's what I mean when I say the nucleus is really, really, really dense. 10 to the 15 times. So that's a wow. Factor of a 1 with 15 zeros after it. Unfathomably large number. So this is something mind-blowing. There are things in nature called neutron stars. They really do exist. Thankfully, there's not any nearby. Just to give you some perspective, the Earth's density is about 5 times 10 to the 3 kilograms, 5,000 kilograms per cubic meter. So take a cubic meter of dirt, and that's how much it weighs. Or that's the mass of it. Well, the density of a neutron star is 10 to the 17 kilograms per mass per cubic meter. 10 to the 17. Now, if that doesn't blow your mind, I don't know what will. 10 to the 17 kilograms per cubic meter. Now, a neutron star is about 20 kilometers or 12 miles or so in diameter, but it has the mass of 1.5 suns. Take all the mass in the sun and crush it down to a sphere of radius about 6 miles. Imagine that. So that means that a neutron star is so dense that 1 teaspoon would weigh 1 billion tons. A teaspoonful of it. In other words, take a teaspoon of the neutron star and put it in a uniform gravitational field of 9.8 meters per second squared acceleration, and you get a weight of 1 billion tons. Interestingly, if you were on the surface of a neutron star, gravity would be 10 to the 11 times that of the Earth. All right, so I hope your mind is blown by this. These facts on this slide I stole from NASA. Just to give credit where credit is due. Okay, so the density of a neutron really is kind of mind-blowing, and the density of a neutron star is not quite there, but it's very, very close to it. Basically, a neutron star is a gigantic neutron. Excuse me, nucleus is basically a gigantic nucleus. All right, here's a question. Since protons are positively charged unless they repel each other, why doesn't the nucleus just fly apart? And the answer is that there's another force. It's called the strong force. Physicists have sometimes been criticized for not having too much creativity when it comes to naming things. But for better or for worse, this thing is called a strong force. It's different from gravity or from electromagnetism. It's one of the 4 basic forces, the other being called, again, not very imaginatively, being called the weak force. The strong force is the one that holds the nucleus together. It's an attractive force between nuclei, and it really acts only at very, very, very small distances, like on the order of 10 to the minus 15 meters. At distances beyond that, it essentially isn't there. By the way, 10 to the minus 15 has a name. It's called a femtometer. If I remember correctly. Hope I get that right. Now, in stable nuclei with many protons, you need to have many neutrons in order to keep the nucleus together. In other words, you need the neutrons there to provide the strong force to hold it all together. So yes, the protons are repelling each other, but they're held together by the strong force. And if you have many, many protons, you need more neutrons to give more strong force to apply, to hold everything together. If you graph the number of neutrons that occur in stable nuclei versus the proton number, you have basically the same number up until you get to about 20. And beyond 20, you get more neutrons in there. So this is the illustration of this claim here. That if you're, for example, at 60, if you're looking at whatever the element is for 60 protons, then you find isotopes with 70 up to 80 neutrons in there. And they have to be there, otherwise it would not be stable. Okay, so that implies that there are situations where some nuclei are not stable, and they do fall apart to some extent. That is radioactivity. So let's now talk about radioactivity. So unstable nuclei just spontaneously spit out stuff. Spit stuff out. And that's radioactivity. This was discovered in the late 1800s, first by a guy named Becquerel, and studied in great detail by the Curies. Okay, so basically this is what they found. There's a sample of something like radium, which is radioactive, and they put it in a lead block, which sort of blocks the stuff that comes out. And they examined what these things were that came out of it. By putting it into a magnetic field, as you can see here, they were able to distinguish three different kinds of things that come out. And they called them, again, for lack of very much creativity, alpha, beta, and gamma rays, or the three letters of the ABC of the Greek alphabet. Excuse me. And so since you have a magnetic field and you have these things going here, you can see that the alpha particle and the beta particle are oppositely charged. Because you see they are affected by the magnetic field, whereas the gamma is not affected by the magnetic field, and so it's not charged. Okay, so we now know that an alpha particle, what they called alpha rays, is really a beam of particles. Alpha particle is a helium nucleus. So it's basically two protons and two neutrons stuck together without the electrons. So it's positively charged. A beta particle is usually an electron. And if you, by the way, if you use your right-hand rule on this diagram, you conclude that the alpha goes to the left and the beta goes to the right, beta being a negatively charged particle. And a gamma ray turns out to be a high-energy photon. Okay, so there are different types of radioactivity which give these, which results in these various things being spit out of the nucleus. So number one is called alpha decay, not surprisingly with that name. It means that the nucleus emits an alpha particle. And as a result, since it spit out a couple of protons, the nucleus transmutes into a different element. So you have the word decay. Decay just means that you lose some protons. So when something undergoes alpha decay, the nucleus loses some protons, and so the element changes into something else. I'll give an example in a minute. Beta decay means that the nucleus spits out a beta particle or an electron. And in this case, the nucleus transmutes into a different element in a process that I'll describe in a minute. There are two kinds of beta decay where an electron or a positron is emitted. So positron is the antimatter partner of the electron. It's basically exactly the same as an electron, except that it's positively charged. There is a reverse version in which an electron is absorbed by the nucleus, which I'll describe. And then gamma decay, the nucleus emits the gamma ray. In that case, the element does not change. All right, let's go through these. Alpha decay, when the nucleus spits out the alpha particle. Here's an example. Radium. So radium normally has 88 protons and 226 neutrons, but it's not stable. So it doesn't have enough neutrons to hold this nucleus together, and so this spontaneously happens. A helium nucleus, in other words, an alpha particle with two protons and two neutrons, spits out or gets spit out, and as a result, the radium loses those two protons and becomes, oh shoot, I don't remember what Rn is. Radium and, does anybody remember what Rn is? What is the name of that? I don't know what it is. Let's see. Can I find it here? The periodic table doesn't give a name. All right, so I don't know what the element Rn is, but it has 86 neutrons. All right. Sorry, I don't remember what that is.
Radon.
Radon?
Radon.
Radium and radon. Okay, very, very good. Yeah, that makes sense. Thank you. I should type that into the slides so I don't forget. It's interesting to note that since the alpha particle is positively charged, the radon turns out to be then negatively charged. So it may undergo some chemistry, grabbing some electrons from things. Or rather, well, giving up some electrons. So if this is positively charged, the radon will be negatively charged. And so it might spit out some electrons. Anyway, beta decay, this is 2A, the first version of beta decay. The emission of an electron or a positron. So the first kind is when inside the nucleus, a neutron transmutes this way. It becomes a proton, and in so doing, it spits out an electron, so that takes away a negative charge, leaving a positively charged proton. But then there's something else. There's another thing spit out, which in this case is an antineutrino. An antineutrino. So neutrinos are really, really tiny little particles. For a long time, people were examining this kind of radioactivity, and they were noticing that energy is not balanced by some of these transformations, and neither is momentum. And they couldn't figure out why. And so maybe they thought that, okay, so now we're finally getting down into atomic scale things that happen. Maybe this is where you don't have conservation of energy anymore. You don't have that conservation of momentum. But famously, Wolfgang Pauli was unwilling to give up these ideas. And so he said, well, no, let's stick with conservation of energy and conservation of momentum and see what it would imply. And so he predicted that there should be another particle that comes out when this happens. But it's tiny, and so it took a very long time for it to be detected. And furthermore, it only interacts with other things in the universe through that fourth force called the weak force, and is very, very weak. So it's extremely hard to detect neutrinos. But after a while, it was actually called neutrinos. By the way, it's called a neutrino by Enrico Fermi. So yeah, Pauli predicted this based on conservation of energy and momentum, and several years later was actually detected. Neutrinos are quite strange, and as I said, they very weakly interact with things. Hold up your thumb. You've got billions of neutrinos flying through your thumb right now. They're just everywhere. But they don't. They just go through your thumb without interacting. Again, go ahead.
Is a neutrino and a neutron the same?
No. A neutron is a big massive particle. That's the N here. And this neutrino, that's the Greek letter nu. It is a far smaller particle. I don't know what the mass of it is offhand, but it's tiny, tiny. It's much less massive than an electron. So there are different particles. There are 3 kinds of neutrinos, by the way. And within our lifetimes, including your short lifetimes as compared to mine, we have discovered that neutrinos change from one kind to another spontaneously. It's called neutrino oscillation. There was a big mystery for a long time. If you measure the neutrinos coming from the sun, it was not what the theory predicted. And so some very, very careful experiments done in the last 10 to 20 years established that neutrinos, as they fly through space, change from one kind of neutrino to another kind of neutrino, which is weird. But there's now a theory for that explains it quite well. Anyway, I'm going off on a tangent. In words, the neutron, a neutron in the nucleus becomes a proton, and in so doing, it spits out an electron and an antineutrino. This happens with carbon-14. Carbon-14 spontaneously becomes, or decays into, nitrogen-14 and spits out an electron and antineutrino. We'll talk more about the decay of carbon-14 in a minute. It's also possible for a proton in the nucleus to spontaneously become a neutron, and in so doing spit out its positive charge in the form of a positron. In this case, a neutrino, not an antineutrino, but a regular neutrino comes out. I think in the next chapter we'll talk about antimatter. An example of this is neon 19 becomes fluorine 19. It spontaneously spits out positrons. Okay, and then there's a third kind of beta decay. It's kind of like a beta decay in reverse. The nucleus absorbs one of the orbital electrons into it. This can sometimes happen. Example is beryllium. Beryllium-7 can snag the innermost electron, orbital electron, and then become lithium and spit out a neutria and so do it. So basically, beta radioactivity involves electrons or positrons. Right, here's the more general way of saying that, you know, the neutron absorbs an electron and then the becomes a different element like this. Okay, then finally, gamma decay. In this case, you have a very energetic photon that is emitted from the nucleus. And why? Well, because the nucleus has different energy levels, just like orbital electrons do in an atom. Remember that we were talking about the hydrogen atom, and we talked about how the electrons occur in different energy levels. And when an electron transitions from a higher energy level to a lower energy level, it loses energy, and it loses energy by spitting out a photon. Well, the nucleus does the same thing, except that the energy levels are much bigger. So in gamma decay, a nucleus in an excited state decays to a lower energy and emits a photon, but it does not change what the element is. So the energy levels of orbital electrons, so these are the electrons involved in ordinary chemistry, and the ones that we talked about with the hydrogen atom and the Bohr model, those energy levels differ by 1 to 10s of electron volts. Remember that the lowermost electron level, energy level for the hydrogen atom was 13.6, negative 13.6 electron volts, so 13 or so electron volts. But the energy levels of a nucleus are like kilo electron volts up to mega electron volts, several orders of magnitude bigger. And so when there's a transition, the gamma ray, the photon that comes out has very much, a whole lot of energy, so much energy that we're in the gamma range, gamma rays. Okay, let's talk about how one quantifies radioactivity. Let n be the number of nuclei that have not yet decayed. And by decay, again, I mean spit out a particle the way we've described. The rate at which nuclei decay is called activity. And it's just this ratio, the number of nuclei that decay in a certain time, delta t, divided by delta t, where delta t is small. And one puts a absolute value here because delta n is usually, delta n is a negative number because you're losing the number of undecayed nuclei. But you put absolute values so that reactivity is a positive number. Units, which are further discussed in the next chapter. Becquerel, in honor of the first guy that discovered it, radioactivity, that's 1 decay per second, which is kind of a ridiculous unit. And so more practical is the Curie, which is like 10 to the 10 decays per second. So 1 gram of radium has an activity of 1 Curie, which is 3.7 times 10 to the 10 decays per second. Here is Mr. Becquerel, and here is Madame Curie. I didn't have a picture of Pierre Curie, who also was involved here. I should put a picture of him too. Okay, the rate at which nuclei decay, which is this fraction here, is equal to this, and it's proportional to the number of nuclei that there are there. So the more nuclei you have, the more, the higher the rate at which they decay, because you have more of them. And it's negative because in the way it's formulated here, n is the number of undecayed nuclei, and so that number goes down. So starting with this, you can write down what the activity is, and that's by definition equal to the absolute value of that left side. And so the activity is lambda n. Lambda being, what did I say it was? I didn't give it a name. So lambda is a rate constant. Now you can use calculus to solve this equation for n, and the result is this, that the number of nuclei as a function of time, decays exponentially. So n0 is the number of nuclei you have at time 0. As time progresses, it's multiplied by this factor of e to the minus lambda t. Combining these together, then you have the activity. The activity is whatever it is at time 0, and then it also decays exponentially. So in this equation, as I said, the n is the number of nuclei that have not decayed at time t, and 0 is the number that you started with. And there's the name for lambda, it's the decay constant. It's, as you notice, that it's in units of inverse time, because the exponent has to have no dimensions. So for example, the decay constant could be in units of 1 over days, or 1 over seconds, or 1 over years. Anyway, the graph of the number of nuclei that have not decayed, called parent nuclei, decays exponentially, as you see here. In this case, I'm plotting the decay of carbon-14 as a function of years. So you start with a certain number. After 5,730 years, you've got half as many of these parent nuclei that have not decayed yet. So that's what half-life is. Half-life is the amount of time it takes to have the number of nuclei that have not yet decayed. As I said, for carbon-14, that half-life is 5,730 years. Half-lives for radioactive things can range from seconds to really, really long times, millennia. Okay, so how does one relate the half-life, which is denoted with a capital T with a subscript half, to this decay constant, lambda? Well, you just plug in NO over 2 on the left side of this equation, plug in T1/2 for the time on the right side of the equation, and then solve that equation. So half-life is then log 2 over lambda, or you could solve it for the lambda in terms of the half-life. So these are useful things to have, because you often can look up the half-life of things, and you often end up needing what the decay constant is. So they're related this way. Here's an interesting story. You've probably heard of carbon-14 dating. That does not mean that carbon-14 went on Tinder and found another element to date. It is a way of, boy, I amuse myself. It is a way of determining how old certain things are, certain biological things are. And here's the story. Most carbon is carbon-12. The vast majority of it is carbon-12. As we've said before, there's a radioactive isotope of carbon, that's carbon-14. And carbon-14 decays, as we said, into nitrogen. The half-life is 5,730 years, as we just saw. The interesting part is that carbon-14 is continuously produced in the upper atmosphere. And that's because the Earth is being rained down upon by cosmic rays. So cosmic rays are just particles, energetic particles that come from space. And they just rain down on the Earth all the time. So this cosmic radiation, it's really predominantly a bunch of protons. But it can be larger things, and it can be gamma rays. But anyway, all this cosmic stuff that comes from outside of the Earth strikes the atoms at the upper part of the atmosphere, breaks them apart, and so then you have a bunch of energetic neutrons flying around. Those neutrons can hit nitrogen and convert it into carbon-14. So you can have this process going on, and it does go on continuously in the upper atmosphere. And then this proton here goes on and does other things. But this particular process goes on at a well-established rate, and we know that that rate has not changed over eons. As a result, the ratio of carbon-14 to carbon-12 in the atmosphere is pretty much fixed, because the rate at which this carbon-14 is produced kind of matches the rate at which it decays. And as a result, there's a ratio of carbon-14 to carbon-12 in the atmosphere of this, 1.3 to 10 to the minus 12. That's the factor of all the carbon-12, which is carbon-14. So not very much of it when you look at this number. But remember that their atoms are really tiny, and there's a lot of them. here's the thing. Here's the story. Biological things use carbon, but they don't distinguish between carbon-14 and carbon-12. But biology is based on regular chemistry, which involves the orbital electrons, not the nucleus. So biological things don't distinguish between these two forms of carbon, and they just take it up as if it were the same. So while something is alive, the ratio of carbon-14 to carbon-12 in the biological object, in the body of the animal or the substance of the tree, that ratio is fixed because it's continuously taking up carbon and continually getting off carbon. But when it dies, it stops taking up carbon. And then, as a result, the amount of carbon-14 that's in it, that's in the dead body or the dead tree, starts to decay, just the way it normally does. But it doesn't take up any new carbon-14. So if we measure the ratio of carbon-14 to carbon-12 in, for example, an old bone, then we can calculate how long ago that bone stopped living. Now, how cool is that? I will answer that question, and I will say that it is very cool. Isn't it cool? All right, let's do some examples, and I'm going to begin with an example based on this carbon-14 dating. So some bones discovered in a cave have carbon-14 activity at this rate, so 0.242 becquerels per gram of carbon. Remember, a becquerel is 1 decay per second. So this bone is exhibiting 0.242 decays per second per gram of carbon. The question is, how old are the bones? All right, so let's go through this. We'll consider 1 gram of carbon. Again, the vast majority of it is carbon-12. There's some carbon-14 in it. But let's estimate the number of carbon atoms in that 1 gram by assuming that it's all carbon-12. Not a bad assumption because this ratio, as we said, is tiny. Now, 12 grams of carbon-12 is 1 mole of atoms, right? You know that from earlier in the semester or from chemistry class. So 12 grams is 6.02 times 10 to the 23 atoms of carbon. So if we have 1 gram, take that many atoms and divide by 12, right? And so 1 gram is 5 times 10 to the 22 atoms. Okay, so that's how many atoms we're talking about in a gram of carbon. When the bone was alive, the ratio of carbon-14 to carbon-12 was this number, which I reported earlier. That's because of the processes in the atmosphere. This ratio is pretty much fixed, and that's the ratio that was in the bone when it was alive. And so the number of carbon-14 atoms that was in that 1 gram of bone when it was last alive was the number of atoms times that ratio, times that number. And so that gives us 6.5 times 10 to the 10 atoms of carbon-14 in 1 gram of this bone, of carbon in this bone, when it was last alive. Since then, the number of atoms has decreased because they spontaneously decay and become something else, become nitrogen. All right, so the activity of 1 gram of bone when it was last alive is this, right? Lambda times N0. We know what N0 is. Lambda we can get because we know what the half-life of carbon-14 is. Remember that activity is the number of decays per second, and the units is becquerels, right? 1 decay per second. Lambda is a decay constant. And we can get lambda knowing that the half-life is this. We derived this earlier, that the decay constant is related to the half-life in this manner. So we can plug those numbers in, and we get the decay constant expressed in terms of inverse years this way. And if we want, we can convert it to seconds. This is 10 minus 12 seconds. Okay, so here's the decay constant that we got from the half-life. We know that when it was last alive, the bone had this many atoms of carbon-14 per gram of carbon in it. And so we can find out the activity when it was last alive. Just multiply these two numbers together. And that activity is 0.25 becquerels. That was the activity, the radioactiveness, if you will, of 1 gram of carbon in the bone when it was last alive. But now, the activity is 0.242 becquerels, a smaller number, right? Okay, so we know that the activity dies off exponentially with time in this way. We can solve that equation for the time. We know everything on the right. So we know the decay rate, that's this number here. The activity now is this number. The activity when the bone died, we just got on the previous slide. So plug in all those things, and we conclude that the bone died 269 years ago. Isn't that cool? I just think that's really amazing that we can do this and estimate how old things are and figure out how old petrified wood was and things like that. Now, of course, there are complications to this simple picture, but this is the basic idea of what carbon-14 dating is. Okay. If you have questions, type something into the chat. Otherwise, I'll go on and do another example. I have a couple minutes left. Actually, before I do that, I'm going to take the attendance screenshots. Okay. There we are. So 1/seconds is hertz, whereas for activity, it's not just 1/seconds, it's decays per second. So yeah, it's kind of the same unit, except that when you're talking about activity, it's specifically decays per second and not other things per second.
So it's almost like saying a radian per second, even though radians are dimensionless? Never mind.
I guess in some sense. But when you say becquerel, you're specifically talking about the decay of a nucleus per second. When you say hertz, you're talking about things per second. So yeah, you could say that the activity is a certain number of hertz, but you don't. You say becquerels. Whereas if you're talking about the angular velocity of something, it's a certain number of, oscillations can be oscillations per second, and that's in hertz. Okay, but yeah, they are, 1/seconds is kind of the same. Did I get okay, I got the screenshot, so I'm not going to go back to the slides and continue and do yeah, I got some minutes I can do this. Here's the next example. So radioisotope 131I, so iodine 131. It is used to diagnose thyroid conditions. So you eat this stuff, and the biology of your body concentrates the stuff into your thyroid, and then it can be imaged, and etc. Okay, a hospital receives a shipment of this iodine 131 with a certain initial activity given by here. So 3.7 times 10 to the 10 becquerels. After 2.5 days, several patients are to be given doses of this much activity each. So you want to know the initial dosage. You want it to be this, 1.1 times 10 to the 9 becquerels. The question is, how many patients can you treat with this sample that was received? So if you're a radio technician working in a hospital, this is the kind of thing you need to know. All right, so what's given is the initial activity of the sample. And we can look up the half-life of iodine 131, and it is 8 days. So in sharp contrast to the 5,000 or so years of carbon-14, the half-life of iodine 131 is just 8 days. Okay, so given this formula now and these two facts that we looked up and were given, we can calculate the activity of the sample 2.5 days after we got it. Let's plug it into this formula. But yes, notice that the formula requires the decay constant, which we can get from the half-life in this way. So remember this relationship here, lambda and the half-life are related this way. So we get the decay constant, and then we plug it into the formula along with the given initial activity. And so after 2.5 days, the activity is now 2.98 times 10 to the 10 becquerels. So it went from 3.7 to 2.98 times 10 to the 10 becquerels in 2.5 days. Okay, that's what this says. So now, imagine this. If you have this sample and you divide it equally into 2 parts, each part would have half of the activity. Because remember, activity is the number of decays per second, and that's proportional to the number of atoms that you have. So if you have half as many atoms, you have half as much activity. Right? So if we divide the activity of the sample by the desired activity of each part, then you get the number of parts. Right? So we take the 2.98 times 10 to the 10 becquerels of activity, which it has 2.5 days after we've gotten it, divided by the desired activity, 1.1 times 10 to the 9 becquerels, and you get 27 pieces. So that shipment, 2 days after it was received, can be used to treat 27 patients. Make sense? I hope so.
Yes.
Okay, I'm pretty much out of time at this point, but there's another simple example. It's a little easier than the previous ones, which I'll just leave in the slides. It just lets you, it goes through a calculation of how many nuclei are there present and other things. I did them sort of in reverse order because the more interesting ones are the more complicated ones. This last one is a little simpler. But that's it. So thank you, everybody. I hope this was useful. And let me also remind you to please, if you don't mind, do the student evaluation of teaching between now and I think there's some time after the end of classes for you to do it. But I'd certainly appreciate that. It would be helpful to me. That's it. Have a good day, everybody. See you next week. I can stick around if anybody has additional questions. Otherwise, see everybody later.
Are you going to do an office hour?
Yes, I'll do an office hour. I'll post information about that most likely tomorrow.
Okay.
Yeah, it'll be tomorrow.
All right, thank you.
I will post the slides. I will post a recording of my office hours and the recording of this. I also have the YouTube channel, in case you want to see the YouTube channel. Feel free to tell your friends in other recitation sections. The last recitation is next week. Thank you for your comment, Julia. If the neutron stars don't exist in our solar system, how do you think we found them? We know them from their gravitational effects, and they're certainly not in our solar system, or we would absolutely know about them, because imagine having an extra mass equal to 1.5 suns just present there. We would definitely notice it. We know they exist in other parts of the galaxy, I guess, because of their gravitational effects on things and radiation that we notice from it, and the size of it that we can infer, things like that. We know that they exist. I'm not an astrophysicist, so it's not my area of expertise, but they are really pretty amazing. Hopefully neutron stars is not something that you apply to your everyday life, but it is fun to think about it every day. So, okay, see you guys later. I'm going to stop the recording now.